Hello friends, welcome to this session. In this session, we will try to understand the topic of types of column, various types of columns, and also the Eulers theory, which is specifically used for the long columns. So there's two topics we will try to understand in this particular video lecture. Let us start with the types of column for because we have started unit number 6, which is axially loaded and eccentrically loaded columns, and our main focus is on the column because the loads are acting onto the column. It is axial or it may be eccentrically loaded, and also our column is a compression member. So it is very important to first of all understand the columns, and this column is a structural member which is used as a vertical member. It is used in a structures, and basically there are various types of the columns are there. In that there are three main important types are there columns, and that classification has been done depending upon the slenderness ratio or length to diameter ratio. So as per that criteria, the columns are divided into three types. Number one, short column. Second is the medium column, and third one is the long column. So first of all, we'll understand the short column. Which column it is called as a short column. So there are some criterias are there depending upon the slenderness ratio or length to diameter ratio. So column which has length less than 8 times their respective diameters. Okay, so if it is a circular column is there, so diameter is there, and whose length of that column is 8 times of the diameter, that value less, or slenderness ratio less than 32 are called as short columns, or this column is also called as stocky struts. And most of the time these short columns are fails by crushing or buckling. When short columns are subjected to compressive loads, their buckling is generally negligible. Okay, whenever there is a short columns are subjected to compressive, at that time the buckling or bending is negligible or is very least value. And sometimes we are not consider or we are not taking for the calculation of bending also, and such a bending is stress is very small as compared to the direct compressive stress. So most of the time the short columns are subjected to direct compressive stresses only. Therefore it is assumed that short columns are always subjected to direct compressive stresses. Okay, so this is the below criteria are given so that we can define our short columns. So length is less than 8d, length of the column, and d is the diameter, and each less than 8d. And also the slenderness ratio criteria, this effective length to least lateral dimensions is less than 32. If it is less than 32, then that particular column we can call it as short column. After that, medium column, the column which has their length varying from 8 times their diameter to 30 times their respective diameters. The slenderness ratio laying between 32 and 120 are called as medium size or intermediate column, and the criteria is the length is between 80 to 30d. Okay, d is the diameter of the column. If it is that value is coming in between these two value, then that column it is called as medium column. And also as like when we talk about slenderness ratio, we can also define the medium column when slenderness ratio is between 32 to 120. So both buckling and direct stresses are significant here, and therefore in design both the stresses are considered or both the stresses are taken into account. Okay, so in the short column we are only considering the direct stresses, direct compressive stresses, but in the medium column the both of the stresses are important. Column may fail by both the stresses. One is buckling stresses, another is the direct compressive stresses. So here for the designing of the medium column, both the stresses are considered or taken into account. Then long columns, length of the column is greater than 30d or 30 into diameter, or slenderness ratio more than 12. If it is there as far as this dimension, then that column is called as long column. Or when we talk about slenderness ratio, whose effective length to least lateral dimension is greater than 12. If it is that value is greater than 12 slenderness ratio, then that column it is called as long column. Or in other way, this 30 diameter, 30D, if is diameter is 30 times, and if your length is more than this 30D, that time also it is called as long columns. They are subjected to only buckling stresses. So now you compare all the three columns. First, short column is subjected to compressive stresses only. Medium column is subjected to compressive as well as buckling stresses, and long columns are subjected to buckling stresses only. Okay, so these only buckling loads are predominant in the long columns. So direct compressive stress is very small, or sometimes it may neglect, or it is very least value, so as compared to the buckling stress, so hence that value is neglected. After that, this is all about the types of the columns. I hope you understood all the three types, that is short column, medium column and long column, and their criteria based on that length to diameter ratio, and also as slenderness ratio also we can define the column, or we can classify the column. So after that, Eulers theory for long column. So specifically, Eulers theory is used for the long columns when only bending or buckling stresses are predominant, or we can say that it is subjected to buckling stresses only. And comparatively, the compressive stresses are very small. So in the long column, this Eulers theory is used. In Euler's theory, the long column is failed due to buckling only. So that's why it is used for long columns only. Okay. So whenever the column is fails only buckling, or only buckling stresses are there at that time, that may be that column may be solved, or we can say analyze by using the Euler's theory. So Euler's theory is basically for only buckling load or buckling stresses only. Effect of compressive load is negligible, means whenever there is a compressive stresses are very less, or very negligible, at that time compressive load is also neglected. So effect totally it is vanished, or totally it is neglected in the Eulers theory. Effect of direct stress is neglected, if because direct stress is induced in long column is negligible, right? So again, though this theory is applicable for long column, and in the long column there is only bending stresses, buckling stresses, direct stresses or compressive stresses are very negligible. That's why this effect is also neglected. The theory is not used for short column, because direct stress is considerable and cannot be neglected. So as we know that in the short column we cannot neglect the direct stresses. So is significant values are there, direct stresses we cannot neglect. So that's why this theory is not used for the short column. It is only used for long column, which has only buckling stresses. Assumptions in the Eulers theory. If you have to design, or if you have to analyze the long column in the Eulers theories, there are some assumptions are there you need to remember for the design. So first assumption is the column is initially straight and uniform lateral dimensions. Second, the compressive load is exactly axial and is passes through the centroid of the column section. Third assumption is the betrayal of the column is perfectly homogeneous and isotropic, means equal type of the materials is present throughout the member or throughout the column, and all the properties are remain same in the different directions, that it is isotropic. Length of the column is very large as compared to its cross-sectional area, cross-sectional dimension. That's why this theory is only used for the long column. The column is long, that is direct stresses are insignificant, means very least, negligible compared to its bending stresses. So bending stresses are important because that are major stresses are induced is the bending or buckling stresses. So direct stresses are very negligible, very least value. That's why it is insignificant for the long column. Plane cross section of the column remains plane and normal to center during buckling. So plane cross section before the buckling and after the buckling remains same, and also during the buckling. Plane cross section during the buckling and before the buckling is remains same. Self weight of the column is neglected. This is also one of the assumptions. Self weight is neglected. The column is failed by buckling only. That's why we are using this Eulers theory for the long column. That's why these columns are only subjected to buckling load. That's why it fails only by buckling. And then some of the limitations of Euler's theory: it is applicable to an ideal structure only, but in practice load applied may not be coaxial, and sometimes whatever the load is applied onto the, or compressive load is applied, that load also it is may not be coaxial, means it may not be along the axis of the column. So these are the some limitations are there, because we are designing, we are using the Euler's theory based on some assumption, but actually in the practice that whatever our requirement is there, that load and your axis of the column is coaxial, but it sometimes it may not have may not fulfill this particular criteria. That is the one of the limitation. It takes no account of the direct stresses. So because definitely, even if you are talking about the actual existence structure, there are both the type of the stresses are induces, that is the direct stresses and buckling stresses are also. But in this particular theory, we are totally vanish or totally neglect the direct stresses. So there is a no account of the direct stresses. That is also one of the limitations when we compare actually on the existence structure. It gives the buckling load for in excess of load, which they can withstand with direct compression. And also there are some sign conventions are there for the bending. Whenever there is a loads are acting, the beam the column is subjected to bending or buckle along its length. So depending upon that buckling shape, the sign conventions are used. So sign conventions for bending moment. So there is a first figure you can see, it is a positive, it is taken, convexity is there. So means bending moment which bends the column so as to produce the convexity towards the, yes, it can show the convexity towards the center line of the column. And this particular sign convention, it is taken as positive when the bending moment bends the column so as to produce the convexity, right? So this particular it is taken as positive. And since second figure you can see that the bending moment which bends the column so as to produce the concavity towards the initial center line. So you can see this vertical straight line is nothing but your column is initially, but after application of the load or whenever the stresses are acting onto the column, at that time this particular column is bent like this. If the shape is like this to the initial center line, then your bending moment, or we can say it is taken as a positive. And when the shape is like that, after application of the loads and stresses, convexity towards the initial uh, center line of the member will be regarded as a negative bending moment. So positive bending moment when the shape is convexity as compared to the initial center line, and when the shape is like this, that is a concavity, here it is a concavity is there, concavity towards the center line, then your bending moment is negative. So here it is also it is written that convexity towards the initial center line is positive and concavity towards the initial center line is negative. Means first figure, if it is a shape is like this, it is taken as positive, and in the second figure the shape of the bending or buckling is like this, that time you have to taken as a negative sign. So this is a this important sign conventions for the bending moment when the stresses are developed into the columns. So I hope you understood. In this particular video lecture we have studied the various types of the column: short column, medium column, long column, and also we have studied the Eulers theory, and which is basically used for the long columns, because as compared to the lateral dimension the length is much larger and only buckling stresses are subjected or induced into the column. That's why this Eulers theory is mainly useful for the long columns which has buckling stresses. And also the limitations, sign conventions we have used, assumptions are there, based on that assumptions we can analyze our member. So I hope you understood this particular topic of the unit number 6, actually loaded columns. Thank you very much.